Welcome back to Bee Spice. In this session, we'll talk about thermocouples. So, in Back to Basics series of videos, we have already covered RTD, and now, as I committed, this is for you thermocouples. Okay. So, what are all the items we are going to talk here? Okay. One is the intro part, just the basics, then the operational aspects, theory. The theory in the sense Seebeck effect, Peltier effect, all those aspects. Okay, Seebeck, Peltier, Thomson. Okay, then components. It's basically a schematic. This is for a freshers, right? And other design technical consideration, very, very important. So at the end of the session, you'll get to know the basics, the operation, the theory, the Seebeck effect, Peltier effect, what is all about it, Thomson effect, what is the components involved in it, and other technical key consideration while designing the thermocouple. Then we are not going to stop with that. We are additionally also going to focus of laws of thermocouple compensation and linearization, very, very important, and types, of course. So the first eight I'll talk about talk in this session, and 9, 10, 11 will focus on the next session. Of course, with the belief that you will support, I have taken this topic again back to basics. I seek all your support, friends, either form, just a pressing a thumbs up button, or subscribing or becoming a member, whatever is, even comment, just a simple comment, how you feel about this theory. It's very interesting, huh? Mark my words, at the end of the session, you will also feel very happy actually. There are many things. Of course, we as a professional, we work, tend to forget the basics, but this will answer all your questions actually. That is my promise. Okay, understanding a thermocouple. Intro. As you know, thermocouple consists of two dissimilar metal wires, metal 1, metal 2, okay, joined at one end. Very simple, isn't it? Yes. So, when the other end of each wire is connected to a measuring element or measuring instrument, the thermocouple becomes sensitive and highly accurate device. Okay, the most important factor to be considered when selecting a pair of materials is thermoelectric difference between the two materials. That is the point here. So a significant difference between these two materials will result in a better thermocouple performance. You got it? Good to go. Right. Few more to add on. Intro part. The construction of a typical thermocouple consists of two dissimilar metal joined at one end in a rigid metal sheath. Okay. So the measuring junction is normally formed at the bottom of the thermocouple housing. Okay. This is the hot junction. This is called measuring junction. Okay. So this is the cold junction. This is called a reference junction. Okay. So MgO, magnesium oxide, right? Yes, surrounds the thermocouple wires to prevent the vibration that could damage fine wires and to enhance the heat transfer between the measuring junction and the surrounding thermocouple. You got it? This is always very important, MgO, just remember. Of course, we have covered this in detail in the data sheet session. Okay, now we'll focus on the operation. Okay, see, thermocouple will cause an electric current to flow in the attached circuit, meaning the circuit to which it is attached, when they are subjected to changes in the temperature, right? So the amount of current produced is dependent on the temperature difference between measuring junction, okay, that is a hot junction, and the cold junction, that is a reference junction. Then the characteristics of the two metals used and characteristics of the attached circuit. It all depends actually. So heating the measuring junction, that is a hot junction of a thermocouple, produces a voltage which is greater than the voltage across the reference junction. So it produces a voltage greater than the voltage across the reference junction. So the difference between two voltages is proportional to the difference in temperature and is measured in voltmeter as a millivolt. Is it right? Clear, friends? Okay, good to go. Now, we'll focus on the theory which we had studied in college days. Yes, in 1821, German-Estonian physicist Thomas Johann Seebeck discovered that when a conductor is subjected to a thermal gradient, that is temperature difference, it will generate a voltage, right? Very simple concept. So this is now known as the thermoelectric effect or Seebeck effect. So here, one thing I want to also tell you, Friends, any attempt to measure this voltage necessarily involves connecting a conductor to a hot end, right? So you need to measure a voltage, right? So any attempt to measure a voltage necessarily involves connecting a conductor to a hot end, right? Yes. So this additional conductor, which also experience a temperature gradient, meaning temperature difference, and also develop voltage on its own, which will oppose the original voltage. Okay, one conductor, another conductor. So this additional conductor will also experience a temperature gradient and this develop a voltage of its own, which will oppose the original voltage. So using dissimilar metal to complete circuit creates a circuit in which two legs generate different voltage. This is the point. Using a dissimilar metal, okay, generated different voltages. So leaving a small difference in voltage available for measurement. Okay. So this is about the theory. Difference increases with the temperature and is between 1 to 70 microvolts per degree Celsius. Okay, friends. So this is about the theory. Okay, now few more to add on the theory. Thermocouple circuit has two junctions. One is the what is that? Measurement junction. That is a hot junction. Okay. Other is the reference junction, which is called as a cold junction. Okay. Typically, friend, reference junction is created where two wires connect to a measuring device. Okay. So this is your reference junction created where these two wires connect to a measuring device. Okay. So at reference junction, there are two junctions. So don't get confused. Just watch out. At this reference junction, there are two junctions. One for here, right? One for each of two wires. But because they are assumed to be at same temperature, that is isothermal, they are considered as a one junction. So the point is, friend, at reference junction, there are two junctions. That is, when you look at it, two junctions. Here one, right? One for each wire. Okay. But because they are assumed to be at the same temperature, they are considered as a one junction. You got it? Yes. So one more point I want to talk here. See, it is this point where the metal change from thermocouple metal. So here it is thermocouple metal, meaning like platinum, rhodium, like that. So this is the thermocouple material normally, right? So it is this point where the metal change from thermocouple metal to whatever metal are used in the measuring device. So in this measuring device, I use typically copper. So this is the point. Just remember, if you are under, I hope you are getting it. See, the hot junction, you have this thermocouple metal. This metal is not all the way going to here. So there is a what? Metal change from thermocouple metal to whatever metal are used in the measuring device. You got it? Yes. So this is where that typically copper come into place. Just remember this. Right. So the output voltage is related to the temperature difference between the measurement junction and the reference junction, which is called the Seebeck effect. You got it? So the Seebeck effect generates a small voltage along the whole length of the wire and is greatest where temperature gradient is greatest. Obvious, right? The Seebeck effect generates a small voltage along the whole length of the wire, not only at this junction. I will tell you why. So this is not only at the junction. So generates a small voltage along the whole length of the wire and is greatest where the temperature gradient is greatest. So if the circuits are of identical material, they will generate identical but opposite Seebeck voltage, which will cancel each other. That is why we should have a dissimilar metal. However, if the wires are different, Seebeck voltage will be different and will not cancel. This point also we need to remember. Right. Good to go. Few more to add on to the theory. In practice, Seebeck voltage is made of two components. Okay. One is Peltier voltage, other is the Thomson voltage. Just remember, Seebeck voltage is made of two components, Peltier and Thomson. So what is Peltier? Peltier voltage generated at the junction here only plus Thomson voltage generated in the wires of the by the temperature gradient. You got it? So that is the difference. Peltier is only generated at the junction. Thomson voltage is generated in the wires by the temperature gradient. Okay. So the Peltier voltage is proportional to the temperature of what? Each junction, while the Thomson voltage is proportional to the square of the temperature difference between two junctions. You got it? So Peltier here, Thomson is here. Okay. So it is the Thomson voltage that accounts for most of the observed voltage, isn't it? Correct. So I'll talk about Seebeck effect. So to sum up, Seebeck effect states that when two different or dissimilar metals are joined together at junction, a EMF is generated at two junctions. This is as a holistic we see the Seebeck effect. Okay, the amount of EMF generated here is different for different combination of metals. Okay, so this is about the Seebeck. Seebeck effect you look at as a holistic because it is nothing but a combination of Thomson and Peltier. That is what. Okay. The Seebeck is nothing but a combination of Peltier and Thomson. So again, friends, Peltier is only here. Okay. Thomson is here. Right. So Seebeck is nothing but Seebeck effect states that when two different or dissimilar metals are joined at two junctions, EMF is generated at two junctions. So the amount of EMF generated is for different combination of metals. Okay, that is about the Seebeck. Then Peltier, as per Peltier effect, when two dissimilar metals are joined together to form junctions, EMF is generated within the circuit due to different temperature of the two junctions of the circuit. Two junctions of the circuit, Peltier. But if you go to the Thomson, as per Thomson, when two dissimilar metals are joined together to form junction, the EMF is generated within the circuit, right, due to temperature gradient, right, but along the entire length of the conductor, within the circuit. That is the point. So in most cases, EMF suggested by Peltier effect is very small because it's only acting here and it can be neglected by making proper selection of metals. Okay. I want to go back again to talk about Peltier to give you a better understanding. Again, I repeat, as per Peltier effect, when two dissimilar metals are joined together to form two junctions, EMF is generated within the circuit. Yes, right, due to different temperature of the two junctions of the circuit. That's it, only at this point. But whereas here, Thomson effect, when two dissimilar metals are joined together to form junction, EMF is generated within the circuit due to temperature gradient, right? But along the entire length of the conductor within the circuit. So that is the point. So in most cases, EMF suggested by Peltier effect is only here, very small, and can be neglected by making a proper selection of metal. You good to go? So the Thomson effect play a prominent role in working principle of thermocouple. So that is the point. So ultimately, this is what I told. Seebeck effect is nothing but Peltier effect plus Thomson effect. You got it, friends? That's all, friends. That's all. So I hope it is clear. Now we go to the component. See, as you can see here, so this is where, the larger Seebeck effect, here smaller Seebeck effect. So literally here nothing is happening. Virtually no voltage developed here. Okay. So nearly all voltage developed across this wire. This is the understanding of Seebeck effect. Okay. Now look at the components actually. You see the measuring junction. This is your wire A, this is your wire B, and this is how the reference junction is there. Cold junction, this is the hot junction. And output voltage is measured here. Very simple, right? Okay. Good to go. A few more on the component side. You can see here, right? This is your heat source. This is where your hot junction, metal A, metal B, and this is your cold junction. And of course, this is the third metal, metal C. Okay. I'll talk about that also. That is for the compensation. I will talk that about detail in the next video. But in this, I'll just touch upon a bit in the next slide. Okay. So this is where the millivolt is measured, friends. Of course, we have shown ice bath and all, but that is not practically possible nowadays. So I will talk why and in the next slide. Okay, this is all about the components. Now we go into the other design consideration. Okay, see a third metal, this is what I told, right? A third metal C may be introduced into a thermocouple circuit and have no impact provided that both ends are at the same temperature. Okay, right. So this means that thermocouple measurement junction can be soldered. This measurement junction can be soldered, brazed, welded without affecting the thermocouple calibration as long as there is no net temperature gradient along the third metal. So that is the pointer. If the measuring circuit metal, see this measuring circuit right here, it's a copper, is different to that of a thermocouple. This is a different material to that of the thermocouple, right? Then, if the temperature of two connecting terminals, if the temp is same, okay, this one and this one is same, the reading will be affected by the presence of this third metal. That is the pointer. You got it, friends? If the measuring circuit metal, this is a copper, is different to that of the thermocouple, metal A and metal B, and if the temperature of two connecting terminals is same, temperature of two connecting terminals is same, the reading will be affected by the presence of third metal. Okay. So now we have to see why. Okay. So the thermocouple output is generated by temperature gradient along the wires, right? Temperature gradient along the wires, not at the junction as commonly believed, right? Right? Okay. So therefore, it is important that the quality of the wire, okay, to be maintained where temperature gradient exists. So for temperature below 400 degree, the contamination of insulated wires is generally not a challenge. But at temperature above 1000 degree, the choice of insulation, the sheet material as well as the wire thickness become critical to calibration stability of the thermocouple. Just understand this. These are some other design which we need to watch out. Okay, right. So voltage generated by thermocouple is a function of temperature difference between junction and reference junction, right? So isn't it? So traditionally, a reference junction was held at 0 degree, okay, by ice bath here. That is what I meant earlier here, right? But the ice bath is now considered impractical and is replaced by a reference junction compensation arrangement. So how that is happening? So this is done by measuring the reference junction temperature with an alternate sensor, typically an RTD. Here in this, we'll have an RTD circuit, which I'll discuss in the next video, wherein I talk about the compensation, right? There I will talk more. So here the point is the ice bath now is considered impractical and is replaced by a reference junction compensation arrangement. So how this is done? This is done by measuring the reference junction temperature with an alternate sensor, typically an RTD, and applying a correcting voltage to the measured thermocouple voltage before scaling to the temperature. Just get to know what is what. Don't worry. In the next video, I'll talk about this in detail. Okay. So now the correction can be done electrically in hardware or mathematically in software. This is what we are going to talk later, how we are doing the correcting and correction. So the low level output from thermocouple, typically 50 millivolt, requires that care to be taken. What for? To avoid electrical interference from motors, power cable. I think this is some typo error, just forget it. Motors, power cable and transformer. So what we have to do, twisting the thermocouple pair, say 1 twist per 10 cm, can greatly reduce the magnetic pickup, right? Additionally, using shielded cable or running wires in a metal conduit reduces the electrical field pickup. So a measuring device should provide signal filtering either in hardware or software, which we are going to talk later, with strong rejection of the line frequency and its harmonics. That's all, friends. Hope you had a very good, concept of this thermocouple. So see you in the next video wherein we talk about laws of thermocouples and laws, LAWS, and of course the hardware compensation, software compensation, and also the types, which is very important actually. Of course, many of us know this, but nothing wrong in having having a refresher session on that. Okay, thank you. And I seek all your support either form, friends, by pressing the thumbs up button or a small, comment, or maybe by subscribing, whatever way. This is just for the channel survival, not for my survival. Okay, I'm already, well settled, no issues. This is for the channel survival. Thank you. Take care. Bye bye.